Hello everyone, this is lecture 4 of the Communication Systems course ENGI 28779. In this lecture, we will continue our discussion of Fourier series. We will talk more on the analysis and how to do the analysis with respect to different signals that are periodic signals, and how the process of applying Fourier series is done to these periodic signals. We will specifically study the square wave signal. But the steps that we show you here will apply to all different kind of signals, triangular signals, sawtooth signals, and others. As long as the signal is periodic, all the steps that I show you today in this lecture will be relevant. We will see the impact of harmonics and what happens as the number of harmonics increase. And we will also see the relevance to it with respect to the bandwidth. We will particularly study DC offset, what it means, why do we have DC offsets, how can we detect the DC offsets, and so on and so forth. And of course, you have DC offsets anytime you use your oscilloscope. So you have that capability to enable it or not. And now we want to give you an explanation of that. And also we'll explain to you time shifting and the impact of time shifting on the frequency domain. So this is kind of a heavy lecture. There's a lot of math in it, but I hope we'll do it gradually and you'll find it beneficial. In lecture number 3, we talked about the characteristics of 4 different signals. So we saw an analog signal, we also saw a digital signal, we saw a periodic signal, we also talked about the characteristics of a non-periodic signal. So just to recap, analog and digital signals, you could determine this by simply looking at the y-axis, right, the amplitude axis, and that tells you if it's an analog or digital. In terms of periodic or non-periodic, you could simply look at the pattern. Is there a recognizable pattern that keeps repeating? And if it is the case, then you could simply find the period of it. If there isn't a specific pattern that repeats, then it's non-periodic. In this slide here, in this lecture 4, I wanted to add 3 other signals to your lexicon of signals, of electrical signals. And the 3 signals that I'd like to introduce to you are even signals, odd signals, and signals that are neither even or odd, right? So they also exist. So what you see here in front of you, this is an example of an even signal. And in fact, the expression here that you have is basically essentially characterizes an even signal. The one that you see next to it is an odd signal. Essentially, what you have in an odd signal is that you have some pattern, and it has a specific symmetry with respect to the origin, whereas an even signal has a symmetry with respect to the amplitude axis, to this axis, right? To this axis. Sometimes we refer to it as the y-axis. So whatever you see here, you see over there. Odd signal, whatever you see here, you see it on the other side flipped, right? So if you were to write it mathematically, you would simply write if your signal looks as such, so let's say we call it x of t, it could be s of t, but here I called it x of t. So if x of t equals to x of minus t, and they are equal, so this value here is equal to this value here, this is an even signal. And if x of t is equal to minus of minus t, then that's a characteristics of an odd signal. So this, you can in fact recognize if a signal is even or odd simply by looking at it. So here, just by looking at it, you know a signal is either even or odd. And don't forget, you look at it by the symmetry. So this has symmetry with respect to this axis, and this has symmetry with respect to the origin. Some signals that are neither, so for instance, this one here, this is a signal. So let's say we give you this kind of signal. This signal is not symmetric in any way. It is not symmetric with respect to the y-axis, to the amplitude axis, and it is not symmetric with respect to the origin. In fact, it has no symmetry. But it's just one kind of possible signal. So this is actually interesting. This expression here. It basically tells you that when you have a signal that is neither even nor signal, you could in fact represent it as as an addition of two signals. So you break it apart. You break it apart, this signal, into a component that is even and a component that is odd. So the question is, well, what is this? How do you get this? It's a bit beyond the scope of the course, so I'm not going to discuss it too much. But if you're interested, if you want to get an even signal of this, what you do is you take x of t, you add x of minus t, and then you divide by 2, and that gives you the even component of the signal. And if you want to find the odd signal of this signal here, you take x of t, you add minus x of minus t divided by 2, and that gives you the odd component. And in fact, if you add both of them, you'll end up getting your x of t. So that's just one way of building a signal that is neither even or odd, right? So you could just build it in terms of these two. So now I think that's enough. If you just know if you're able to distinguish between an even and odd signal and signals that are neither, that's very enough for us to proceed. In fact, this skill will be necessary for us to know to know of, so that when we analyze Fourier series in the next slides, we will be able to simply simplify the analysis. If some of the signals that we will analyze are periodic and they are, let's say, even, then it will simplify the Fourier series analysis. If some of the signals are odd and they are periodic, it will also simplify the Fourier series analysis. If some of the signals are neither, they're not even, they're not odd, but they are periodic, we can still represent it using Fourier series, but unfortunately these ones are the most complicated type and will be longer to analyze, but it's still possible to analyze them in Fourier series. So just knowing this slide, I think it's important. I didn't show it in lecture 3. I added here in lecture 4, and I hope now you know what it means. Okay, let's move on. In this slide, I'm interested to show you some of the ideas behind adding signals together, adding signals that are sinusoidals. So we refer to this, the term that is typically used when we want to talk about the addition of things. In this case, we're talking about the addition of signals. We refer to it as superposition. So you see the word superposition. This falls under the concept of the superposition theory. So here we talk about the superposition of sinusoidal signals. So let's say we give you a bunch of signals, S1, S2, until all the way to Sn of t. So you have n of these signals, and we tell you that these signals are sinusoidals. Now, if you forgot what sinusoidals are, go back to lecture 3, and we talk specifically on sinusoidals. We spent a good time just explaining what sinusoidal signals are. So we say that these signals are sinusoidals, and we add them, right? We add them together in order to form something called an ST. So this is the total, this is the superposition of the signals. Okay, so if we then take the Fourier series of this superposition of the signals, of these sinusoidal signals, well, what you have on the other side, what you have on the Fourier series side in the frequency domain, so again, this is time domain, this is frequency domain, is simply the same thing, except now you are looking at each item in its frequency domain representation. So in other words, you have your first signal, well, this is the frequency domain representation of the first signal. You have the second signal, this is the frequency domain representation of the second signal, and so on and so forth. And we are able to do this using Fourier series. And why are we using Fourier series? Because these are sinusoidals, and by definition, sinusoidals are periodic signals, and therefore we use FS. We use Fourier series, and because they are added here, we could also add them in the frequency domain. Now, why is this possible? Why is this? Well, this comes under the property of linearity, right? So in Fourier series, there's a bunch of properties. One key property that we have when we talk of Fourier series is linearity, right? So if you add some things, different items in the time domain, you would basically have the same thing. You would have the addition of the frequency response of each of the signals.
So this is what linearity is. Also, if you multiply, let's say I multiply this by, I don't know, 5, and this by 3, and this by 7, you will still have here, for instance, 5, 3, and 7. So this also is part of linearity. Okay. Now, one thing that I should completely stress, and I put it here in red so that you really realize this. If we give you a bunch of signals, and these signals are sinusoidals, and you add them, there is no guarantee that the superposition signal, that the total signal that you get is periodic. There's no guarantee. Many people do the mistake here, including graduate students. When I would teach graduate students, they think, and I ask this type of question at different universities, they think it should be periodic because each of these signals is periodic. That's not true, right? So if every item is periodic, and it is periodic because it is sinusoidal, it does not guarantee that this one is periodic. You have to prove it. You have to show it. So we'll talk a bit more on that. But just so you know, and I hope you realize that this is very important. That's why I put it in red. Okay, so let's continue. So I'd like to show you an example here in the time domain of some signal. So let's say we have two signals, just S1 and S2. Let's add them and let's see what the result that we get. So say we have this signal here. You have some signal that is represented, so it's a sinusoidal, right? So it looks like a sine wave, so it's a sinusoidal. It is characterized by this equation. So we know that this is 4 over pi. This is simply the amplitude of it. We'll see it in a second. And we know that it has a radial frequency of omega naught. And we said radial frequency, once you have a radial frequency, you could in fact find its frequency in hertz. So radial frequency is equal to 2 pi f naught, and therefore you have the f naught. And once you have f naught, you could then find the period of the signal, which is simply 1 over f naught, and that's your t naught. And without even looking at this, just by looking at the picture, you look at a pattern. And when does the pattern keep repeating again? So let's say I look from here. This is one pattern, and then it repeats again from here. So it means this is my period. Now you could have also started from here, right? So you could have started from here all the way to here, and that would be your period. Okay. And like I said a second ago, we can find the frequency of the signal by simply doing 1 over the period, and that gives us the frequency of this signal. So frequency of I write f1 because it's signal s1, and f naught, that's the fundamental frequency. That's the fundamental frequency. In this case, it's just f naught because this is omega naught, and it's just this. So this signal here has this frequency f naught. The amplitude, in case you want to see where it is, well, it's just the biggest peak, v peak, your largest peak value of the signal, which is 4 over pi, and this is 1.27. Now, I forgot to add the units here, and don't forget to add your units when you do this in an evaluation. The units are for sure volts, right? So we're talking of a signal in the voltage domain. So this should basically be volts. Okay, so this is time, and this is a volts here. Okay, so let's see another signal. So we have another signal. We have this one here. This is another signal. Just by looking at it, forget about the equation, just by looking at it, it has a behavior of a sinusoidal, whether it's a sine or a cos, doesn't matter, but it's a sinusoidal nonetheless. Here we give you the equation that comes with it. So you have this, you have the frequency of it. So now the frequency of it, the radial frequency is 3 times what you have here. 3 times what you have here, and therefore you will see the pattern being moving a bit faster, right? So if we were to look at the period of the signal, and the period would be to start at some point and look at a full cycle of a pattern. So from here all the way to here, and then you measure it, and then you measure this one here. You notice that this is a third of what you have here. This is a third. If fact, if you don't believe me, let's just take this T naught and put it here. I'm going to just put it in grayscale here, in gray. And if you look, we have how many expressions of the pattern we have repeated in T naught? We have 1, we have 2, we have 3 times repeated. Therefore, just one of the cycle is T naught divided by 3. So this is your period. So now you might ask, well, what is the frequency of this signal? Well, the frequency of the signal, you could simply obtain it by simply doing 1 over the period that you have. In this case, the period is T over 3, and therefore you get 3 F naught. Otherwise, you could have also obtained the frequency by using this. Your radial frequency is 3 omega, and you simply make this equal to 3 omega naught. You make it equal to 2 pi F naught, and that enables you to find your frequency for this signal, which is 3 F naught. Okay, so I hope you see that because it's 3 omega naught, the frequency of this signal is 3 F naught. This is omega naught, the frequency of this signal is F naught. And the amplitude is this thing here, whatever you have here, is 4 over 3 over pi. 4 over pi is similar as this, except now that you divide it by 3. So you're actually shrinking 3 times, right? So this is 1.27 volts, and here the amplitude is 0.42 volts, okay? So that's what we get. So now we're telling you, consider this signal and consider this signal, and let's add them together. What would you get? So if we add them together, you would let's say get something like this, right? So you would get something like this, and this is the result that you obtain, right? So you're simply adding this signal and this signal. And now the question that we ask you is, well, nice, okay, so you were able to add 2 sinusoidals together. Is this signal, is it periodic? Is this signal periodic? There might be a natural tendency to say yes, just as that, you know, just by looking at very short span of the signal in the time domain and assuming it is enough to say that. But in fact, you have to prove it. And a good way to prove if 2 sinusoidals that you add are periodic is by doing the following, by doing the GCD. A GCD stands for the greatest common divisor. Okay, greatest common divisor. So you take the GCD of the first frequency that you have. The first frequency is F naught. The second frequency that you got is 3 F naught. And you could simply plug in the values, right? So F1 is F naught, F2 is 3 F naught. And the greatest common divisor, something that divides both of them, is in fact F naught. So because we actually proved it, we know that the period of this signal is F naught. But if sometimes you might do the GCD of 2 sinusoidals and you won't get anything, right? You won't be able to solve it. The GCD will not give you a result. If you don't get a result, it means that the addition of 2 sinusoidals does not result in a periodic signal. So this is why I put in red here. Sometimes it is periodic, sometimes it is not. You really have to prove that it is periodic or not. In this case, we kind of knew it's going to be periodic because you see inside the sinusoidal, it's already represented in terms of the fundamental frequency. Right? It's already represented in terms of omega naught. Omega naught is the fundamental frequency. So we kind of knew it's going to be periodic. But sometimes if I give you, I don't know, let's consider, for instance, sine of 6 pi t plus sine of 7t. Right? So I didn't show it here, but let's just consider this, for instance. I'm just cooked up this on the fly right now. And if you have sine of 6 pi t, that's a frequency of 3 hertz. And sine of 7t, that's a frequency of 7 over 2 pi. Now, if you look at both of them, there is no multiple. There is no multiple of each other. It's just not possible. So adding these 2 signals, although each of them is periodic, the addition of both of them will not produce a periodic signal. And we did this because of the GCD. So this is a very powerful tool. And in fact, many people don't know, or just, I don't know, they assume because you add 2 sinusoidals that the result will be periodic. So just keep that in mind. Okay, so what is the period? Well, you could, since we determined that it's periodic, and we determined that the period is F naught, then we could in fact realize that the 1 over F naught is the frequency is F naught, that 1 over F naught will be the period. And if we put it here, well, let me just put it for you. So this is what we get, right? So we get this, and in fact, this period is the same thing that you have here. So it is periodic, and this is exactly what we get, okay? And we got this because we simply did the 1 over f naught, and that gave us the period. Okay, so now that's fine. How do we look at this signal in the frequency domain? So let's see how to look at this in the frequency domain. So sometimes looking at a signal in the time domain becomes a bit complex, but you still need to have these skills. You need to have these skills to actually go from an equation to a picture, to a figure, and from a figure to an equation, and to get data from a figure. Right? You look at a signal. What can you identify within a signal? You look at a signal. What can you identify here? How is this different from this? You need to have these kind of skills. And this comes with practice and by doing many problems in this area. Okay, so let's look at the frequency domain representation of these signals. Let's look at this one here. So we have this thing here, and remember we did this in lecture 3 that if you have a sinusoidal, the frequency domain of a sinusoidal will simply be a spike in this frequency. So this is frequency f naught. It will be a spike here. So it will be a spike at the frequency f naught, right? It will be a spike at the frequency f naught, and the value of the spike is the value of this 4 over pi, and 4 over pi is 1.27 volts. That's just the value of this 1.27 volts. Now here in this representation we have, it's a frequency domain, right? So the x-axis is in frequencies, and the y-axis usually, like we said, if you use a spectrum analyzer, not usually, in fact, all the time, whenever you use a spectrum analyzer, the y-axis will give you the result in dBm. In this case, we're not using a spectrum analyzer. We're just doing it analytically. We're still using voltage. So this is in voltage. It's 1.27 volts. So it's very simple. For this sinusoidal, this is the result that you get in the frequency domain. I hope this is clear. Now, what about this one here, the next one? Well, the next one is kind of similar. We know the frequency it operates at. It operates at frequency 3f naught. So you're at 3f naught. There's nothing at 2f naught. Nobody gave you anything at 2f naught, so you don't do anything. F naught is also not given. This thing here, this signal 2, is only related to 3f naught. By the way, I realized I forgot to put the sub here. It should be sub S3f. And this should be S1f. So I forgot to do that. I apologize. But basically, this is what you have. And the voltage, the value that you have, the voltage, if we consider voltages, not dBms, then it's simply this thing here, 4 over 3 pi, which is 0.42 volts. Okay? And if you add both of them in the time domain, well, in the frequency, you simply add these two spikes together. And when you add two spikes together, this is the result that you get. So this is your result that you get. So this is in fact equal to S1, this thing here, S1f plus S2f, and this is what you get. You simply put them together, and this is what you get. Now, let's say in an evaluation, I or some other professor asks you, well, that's nice, it's good effort. You were able to go from time domain to frequency domain, but can you represent your result in dBm? Okay, so if that's the case, we always said the process to go from voltages, from peak voltages to dBm is always the same, right? So there's 5 steps that you have to follow. Step 1, find the voltage, the value, the peak value, the peak voltage. Then from the peak voltage, determine the RMS voltage. Once you have the RMS voltage, determine the average power of the signal using Watt's law. Once you have the average power, determine the dBW, the power in dBs, so in dBW. And then once you have the result in dBW, change it to dBm. So it's just 5 steps, right? So that's generally how you do it. Every time you have a value in peak voltage, you want to go all the way to dBm. You follow the step. So find the RMS, find the P average, find dBW, and then find dBm. Sometimes we give you, maybe we provide you the voltage, we provide you the peak to peak. Well, you should realize what peak to peak is. Peak to peak is simply equal to 2 times V peak. So that's just common sense. And I think we talked about it in lecture 3 as well. So, but if you recall in lecture 3, we actually derived an equation that will do all these steps automatically for us, right? So if you recall from lecture 3, this is the important result that we got. So instead of doing all these 5 steps, you kind of get something like this, okay? You put your V peak here, and you put the internal resistance of the spectrum analyzer, the RF input of the spectrum analyzer. You put it here, the internal resistance. But you could always, if it's not given to you, you could always assume 50 ohms. This is a reasonable number, and this allows you to find the values of your spikes in the frequency domain in terms of dBms. So if we do this, let's see what we get. This is what we get is a 12.1 dBm. So 12.1 dBm and 12.1 dBm. I put it in both pictures here. And so again, how did we get 12.1? Well, we plugged in 1.27 here, and here we put in 50 ohms, and we do the calculation, and this is where we get 12.1 dBm. And if we do for the 0.42 volts, so we enter 0.42 volts here, still it is 50 ohms. We're still using the same spectrum analyzer device with an internal resistance of 50 ohms. And we do the calculation, and this should give us 2.5 dBm. And that's it. So now we have kind of a full circle of what we obtained by looking at the superposition of sinusoidal signals. So this is a good example that shows you when you add 2 signals. Now, certainly here we only looked at the addition of 2 signals. Sometimes, so we only added 2 signals that are sinusoidal. And we noticed that this is sinusoidal, this is sinusoidal, this is periodic, and also this is periodic. We were able to prove it. But this is not necessarily always the case. So if you begin with a signal that is periodic, and you use Fourier series to break it down, you know that each of the breakdown of the signals will be periodic. But if you begin with sinusoidals and you add them, just whatever sinusoidals is given to you, there's no guarantee that the result will be periodic. So I kind of repeated it a couple of times just to make sure you have this. That's it. I think this is a good introductory before we move into Fourier series. So now you have this here, the superposition of sinusoidals and how we get results in the time domain and the frequency domain. Here we showed you with only 2 signals. And on the previous slide, we saw even signals, odd signals, and neither signals. And I think now with both of them, we could see how to use the Fourier series. So I'm going to show you how to use the Fourier series. On to the next slide. Although we saw Fourier series in lecture 3, in this slide, I wanted to kind of explain more the details of the different variables that you have in the Fourier series equation. So there's a lot of information there. What does it all mean and how it all comes together? So this kind of is the purpose of this slide. And we will look at it by specifically focusing on electrical signals. Right? So Fourier series could be used in just pure mathematical sense, but we're using Fourier series for us, for electrical engineers. So I'll talk about it in the electrical signals perspective. So everything that we show you are either voltages or signals, and we'll put it in that context. So what you see here, this is essentially a Fourier series, right? So this thing here is your signal. This is a signal that is a voltage versus time, so it's in the time domain. And this is a periodic signal. It has to be periodic in order for us to represent it in a Fourier series representation. This is what you have here. This is called the Fourier series representation of the periodic signal. And essentially what it means, it's a mathematical formula, but basically what it means, and we talked about it in lecture 3, is that any periodic signal can be broken down into a bunch of sinusoidals. Sines and cosines, they are both sinusoidals, and we're simply adding these sinusoidals. The only difference is that we have many of these sinusoidals at different frequencies, and at every frequency contribution, at every frequency, there will be a certain voltage contribution. This is what the AK and BK are. So let's go into detail right now. So like I told you before, the signal that we are trying, the electrical signal that we're trying to represent in Fourier series, it has to be periodic. If it is not periodic, forget it. Fourier series does not work. You have to use Fourier transform. Okay, and we said Fourier transform, Fourier series, they're pretty much the same. The only difference is that you could think of Fourier transform as a Fourier series, or rather a signal that is non-periodic, as a periodic signal with a period that goes to infinity. That's kind of an interesting way of explaining it. But for us, we don't care right now. We only care about periodic signals. So this thing here is a periodic signal. Okay, now, why did I put this, the approximation symbol? Why not the equal? The reason is that we are in real life. If we are talking of real life scenarios, we don't put an equal. If you put an equal, it's because you will take infinite summation, a summation that will go forever. But in real life, this will never be the case. You cannot run a summation that will go forever, for infinite summation. If you do that, then you'll end up getting a bandwidth of infinity. And this is not realistic in any way, shape, or form. So we look at it in a realistic way, in a real world perspective, and therefore we put an approximation. So the Fourier series will give you an approximation of your periodic signal. And that's why we put this symbol here. And we put this because we are only taking n harmonics, right? So this, whatever you have here, in here, they go hand in hand. If you have infinity here, then you put equal here. But if you have approximation here, then you put n. N is just some specific integer number. Okay? And like I wrote to you here, Fourier series provides an approximation of the periodic signal with n harmonics. So we consider n harmonics, we put approximation. So some approximation are better than others, so it depends. If you have bigger n in general, this should yield a better estimation. If you have a smaller n, let's say 1 or 2, the approximation will be so-so. It's not the best, right? But if you have bigger n, more harmonics, you will get a better approximation of your signal. And we'll see how we'll show you visually what this means later on in next slides. Okay, what else do we have? We have this thing here, this component here. This component is referred to as the DC or direct current component of the periodic signal. There is no frequency. You don't see any frequency related to this. It's like a battery. You know, you have a battery and the battery has a voltage. It's a 5-volt battery, and you know, it's a specific value. It's a constant value of voltage. Of course, with time, this voltage diminishes, but nonetheless, it is a constant value. That's what DC is, and you saw this in other courses in the past. So this is DC component. And this is how it's represented by some A0 divided by 2. What is A0? Well, we'll derive it. We'll show you how to get A0. It's some constant value that you need to derive, and then you divide it simply by 2. Okay. This is known as the DC component. Don't forget this. This is very important. You'll see how you will also be able to detect the DC component visually. Either by looking at it in the frequency domain, you'll be able right away to detect the DC component, or by looking at it in the time domain, you will also be able to detect the DC component. Both of them will enable you to detect the DC component, and we'll see that later on. What else do we have? Well, here we said that your signal is broken down into even and odd signals, right? So you have a component based on cosine of something, and based on sin or sine of something else, the inside of the sinusoidals, right? So we said we take a periodic signal and we break it down into 2 sinusoidals. One that deals with the even component of a signal, and the one that deals with the odd component of the signal. So let's put it this way: if your periodic signal is an even signal, then right away what you end up doing is you only need to focus on this part here, right? And you will only need to find AK and A0. If, however, your signal is an odd signal, right? If an odd signal, you only need to find this, and this will be 0, and this will also be 0. Okay, so this is why I showed you earlier the definition of even and odd signals, because it will simplify the analysis of Fourier series. So again, if your signal that you want to find the Fourier series equivalent representation, look at it and see, is it an even signal? If it is an even signal, what you do is you need to keep this and you need to keep this, but this part here will be 0. There is no odd component to it. If, however, your periodic signal is an odd signal, you keep this part becomes 0, and this part becomes 0. Okay? And that's how you simplify the analysis. If, however, you have a periodic signal, but it's neither even signal or odd signal, then in that case, you need to find both this component here and this component. And this is one of the most complicated way of representing a signal, a periodic signal, because you need to find both of them. I mean, complicated in the sense that you will spend more time analyzing the signal and finding these values here, the AK and the BK, the coefficients. That's that. So I hope knowing what the even and odd signals is useful, because here you will certainly benefit from it here. What else do we have? Well, we have these things here, AK and BK, as I mentioned a second ago. They are referred to as the Fourier series coefficients. Now, how do you find the coefficients? You need some calculus skills. So essentially, you just do this constant here, 2 divided by the period of the signal, T0, and for BKs, 2 divided by T0. And you simply take this signal, the periodic signal, here, you multiply it by cosine, this thing here, with respect to dt, and then you integrate with respect to t, and you find the result. Now, don't forget, you're not integrating forever. You're only integrating with some window of T0. You choose whichever window of T0 you want to consider. All windows of T0 of your periodic signal would work. So choose something that will make your analysis easy. Here, what you do for BK is this, it's kind of similar, except the only difference is that instead of cos, we put a sine. So if your ST is a odd signal, then in this case, what it means is you will only need to find BK, this thing here. This thing here, don't even waste your time, it will be 0. So if ST is an odd signal, AK will be 0. You only need to derive BK. If, on the other hand, your ST is an even signal, then you only need to find this one here, AK, and your odd, your BK will be 0. Okay, and that's how life is simplified for you. If, on the other hand, your ST is not an even signal, it is not an odd signal, it is, however, a periodic signal, but it's not even or odd, then you'll need to find both AK and BK, and then you simply plug it in the expression here. Okay, what else do we have? We also have the omega naught. So you have an omega naught here and you have an omega naught here. They are referred to as the fundamental radial frequency. So this is the omega naught. This is so essentially, if we were to say what is the fundamental frequency of this signal, of this periodic signal, you could just say it is omega naught. And what is omega naught? Well, you could also represent it as 2 pi f naught or 2 pi over t naught. So this is what is known as the fundamental radial frequency. This is a constant. This is an actual constant value. It does not vary. You just pick, it's a fixed value that you should either have or it's given to you. Okay. What else do we have? Well, now what is only left is these k's, right? These index values, k's. It's a summation, so you keep adding from 1 to the value n. N is an integer, right? It's an integer, like we said. Could be 5, could be 2, could be 4, could be 3. The bigger it is, the better approximation you get, but it's just an integer. So I just want to I did the table here for terminologies because I noticed some people don't use the proper terminologies with Fourier series. So look at this table here, and notice this. If you want to talk about the first harmonic, right? First harmonic is anytime we use a k, index k of 1, we will work in this case with the radial frequency of omega naught or the frequency f naught, and this is referred to as the first harmonic or the fundamental frequency. Okay, so this is what it means. If somebody mentions the fundamental frequency, well, it simply means your f naught.
right? The component, the voltage that you have with respect to the F naught value. If we talk about the second harmonic, it means K is equal to 2, and we're talking about 2 F naught. If we're talking about the third harmonic, we will talk about 3 F naught. The fourth harmonic, 4 F naught. So I guess the one that is generally confusing with students is this one here. So this, don't forget, it has a name. It's either the first harmonic or the fundamental frequency. In fact, people will generally simply refer to it as the fundamental frequency, and just know that, but it's also sometimes referred to as the first harmonic. So I hope this kind of gives you a sense of how the Fourier series is and what it means. Again, we saw this before, but I didn't go into the explanation of every component, and this is what I wanted to do on this slide so that you're familiar with the different values here. So now on the next slide, what we will do is we will use this on an example, on a square wave example, and we'll see how this function, these equations work and how we can derive the Fourier series. Okay, so on to the next slide. Okay, so now we've seen what Fourier series is in detail. I showed you the equations and we went through it. At this point, let's go and have a look at an example. And one of the famous examples that we have in our field is the square wave signal. So square wave signal, this is how it looks like. And so we're in the time domain, and you have your time domain here, you have the voltage here, and it's just a bunch of pulses like this, right? And that's what it refers to by the square wave signal. And so this is what we have, and let's just analyze this. Let's try to obtain the Fourier series expression of this so that we'll be able to show this in the frequency domain. I mean, don't forget, ultimately we're doing all this because we want to show this in frequency domain, and we have no idea how to do this without Fourier series, and that's why we're wasting time and we're doing all this work to figure out the Fourier series of it so that we can see it in the frequency domain. Right, that's the whole point. So let's take it. Let's analyze this signal together. So you need to take a deep breath. It is a bit long. There's some math involved, but we'll go through the steps together. So first thing first, you have the two states for the voltages. So if the voltage is here, it's V peak. That's what it means. So let's say it's 5 volts. And if you're in the bottom, it's minus V peak, whatever. It could be minus 5 volts. Okay, that's just the value of it. The other thing that we should maybe ask before we continue is this waveform periodic? So simply by looking at it, there is a pattern. Let's say this pattern here, and it keeps repeating. You could just take a copy paste everywhere. So the answer is certainly yes, it is periodic. Then let's continue and let's have a look at, let's say, one period. So this is just one period. I highlighted here in blue, but in fact you could highlight any period of your choice. This is just one of them. This is one pattern, and this pattern keeps repeating. That's why it is a periodic signal. Because we have a signal, it is periodic, then certainly we can find its period, and its period is basically just the time here. This is the period of the signal. Now that we have the period of the signal, we could in fact obtain its fundamental frequency. So this is the period of the signal. The period of the signal is T0, and therefore the fundamental frequency is simply 1 over the period. And the fundamental radio frequency is simply 2 pi times the fundamental frequency. Right? So don't forget, this is the terminology used for anything with T0. Okay, what else do we have? Now, maybe we could ask another question. Is this signal an odd or an even signal? So simply by looking at it and while remembering the slides that I showed you earlier in this lecture, first slide that we saw in this lecture, this is certainly an odd signal. There's a symmetry with respect to the origin, so it's symmetric with respect to origin, and certainly this is an odd signal, okay, not an even signal. And we said if we have knowing if a signal is even or odd will simplify our life with Fourier series. If a signal is neither odd or even, it's the worst case scenario. It's going to be a very long analysis.
But if a signal is odd, it's going to be much easier. Or if a signal is even, it's going to be much easier because some of the terminologies can be canceled in the Fourier series. So let's do this right now. If I just bring the Fourier series that I showed you on the previous slide here by definition, I'll just bring it back again here. I just rewrote it. So the only difference is I added the subscript here, SQ for square, just so we know that we're going to derive it for the square. And like we said, this is an odd signal. And because it is an odd signal, the even component is gone. The even component is this. This will be 0. This will be 0 because this AK will be 0 and this A0 will be 0. So this part is gone, this part is gone, and therefore we could simply simplify our life and right away represent it as such. So now we have, basically we know how the Fourier series will look like. The Fourier series will be of this form. You might think that we're done, but in reality we're not very done. In fact, we're not really done because the most challenging thing in figuring out the Fourier series is determining these coefficients. So in this case, this BK. This BK is what is somewhat long and it takes some effort to derive. And we're going to do it here, but in general, it's always a bit time consuming to figure out this BK, and you need to have some mathematical baggage as you do it. But we'll do it together so you see how it's done. So by definition, and we showed you this on the previous slide, BK is equal to 2 over the period of the signal. So T0, this period here, we just bring it T0. And we take the integration over a specific period. Any period that you want, it doesn't matter. You could maybe take it under this period, you could take it under here, pick whichever you want. In general, it is not a bad idea to pick it around the origin. This is the origin. So if we consider this region here, we'll take it from minus T0 divided by 2 until T0 divided by 2. But we have to do it piecewise because there is a discontinuity between this one and this one. There's a sudden jump. So we have to do it piecewise. We have to break the integration in 2 parts. Do this first and then do the other one. Okay, so by definition from Fourier series, the BK is this, integration over a specific period. We bring in the signal here. We multiply it by the sinusoidal with the different harmonics of the that we have, the K omega naught T, and we do the integration with respect to T. So this is just a very basic calculus attempt that we have to do here. So let's see how it's done. What we will do is we will break the integration in 2 parts because, like I said, there's a jump here. Right? There's a sudden jump from this end to this end. So we'll integrate from minus T0 over 2 until 0, and the value of the signal is minus VP. That's why instead of ST, I enter minus VP here. I enter this thing here, the sinusoidal with the different harmonics, dt, plus this component here, which is from T0 until T0 over 2. And the value of the signal is here, which is VP. This is a constant, but it's negative. And then I enter the sinusoidal and dt. So this is what we get. This is called a piecewise integration. So you have to use piecewise integration because there's the sudden jump. So just be careful on that. It's not continuous directly. Okay, so let's continue. What else do we have? Now let's just maybe clean up a bit this equation. VP is just a constant. VP is just a constant. They're the same. So I could in fact factor it outside this bracket here. I could factor it outside. So let me just put it outside. So I have 2 V peak over T0, and the minus I could also put it outside the integration. So I put it here. I'm integrating from minus T0 over 2 until 0, and then we have this, and from 0 to T0, and we have this. So I hope going from here to here, it's understandable. It's straightforward. Now the question is, how do we integrate a sinusoidal? Well, if you remember from calculus, if you do the derivative of a sine, you get cosine. And if you do the derivative of a cosine, you get minus sine. And therefore, if you integrate sine, you're supposed to get minus cosine. Okay, so and of course you have a constant. This k omega naught is just a constant in the integration. So I'm not going to go through this. This is something that you've seen in calculus. But basically, this is what we're invoking, right? This is kind of, I opened the sidebar here just as a reminder that if you have some integration of some constant, let's just call it alpha, times the variable itself, t, dt, then it's going to be minus cos, here, whatever you have inside, divided by the constant, plus whatever, some useless constant that we add. But because you're taking the difference, this constant that we have no idea what it is, it's going to go away. Okay. So we're going to use this for each of these piecewise integrations. So let's just use it and plug it in. So we have, this is what we have. We have our 2 v peak t naught. Instead of this, I enter this thing here. But my alpha here is simply the constant part, the k omega naught. K omega naught, I simply enter it, I divide by that, and I move from minus t naught over 2 until 0. And on the other side, I also do it, and I move from t equal to 0 to t over 2. Okay? Now that we have this, we could perhaps also do more cleaning up. K or omega naught has no relationship to t, so I could in fact take it outside this square bracket, right? So I could take it outside the square bracket. The minus also I could take it outside, so minus and minus becomes a plus, so this becomes a plus. This I could just put it in the bottom, so I have 1 over k omega naught, and the only thing that varies with respect to t is this thing here, the cosine. The cosine with the sinusoidal, and I just rewrite it like this. Over here is the same thing. The minus, I could take it outside, so I have a minus. The k omega naught also is a constant, so I could just take it outside. And I end up with this in here. Okay, let's see what else we could do. Well, as a next step, we could also, this and this is common on both sides, so I could simply factor it outside this bracket. And I could put it outside in this multiple. So I could just put it there. So we have 2 v peak t naught, and this I could just factor. So we have k omega naught, so it's all outside. And the inside of the bracket is this, right? This is what we have. It's just the inside of it, minus the inside. So I'm basically rewriting. I'm just reorganizing things. Now, what is interesting to observe is the following, is that at this point we could simply plug in the values, right? So when you have a certain result of an integration and you have different values that goes from minus t naught over 2 until 0, it means you enter 0 first, minus the bottom part, minus this, and you do the same thing on the other side. So you simply enter the values. This is what we get. So you enter 0, it becomes close to 0. You enter minus t naught over 2, you get this. And you do the same thing on the other side, you get this. Be careful with the brackets. Keep your brackets everywhere so you don't forget a minus anywhere in here. Now, one thing that we should remind you is that if you don't forget what this is. This is the radial frequency. The radial frequency is equal to 2 pi f naught. So f naught is the fundamental frequency, or it's also equal to 2 pi over t naught. And therefore, if you do the radial frequency times t naught, it's only equal to 2 pi. So this is something that is always true. So here you have here omega naught t naught. Well, you can simply replace this by 2 pi, right? So and here you have omega naught t naught, you could replace it by 2 pi. Here you have omega naught t naught, you could replace it by 2 pi. So this will simplify a lot here. So 2 pi here, the 2 and the 2 will cancel. You'll only be left with a pi in the bottom. 2 pi here, the 2 and 2 will cancel. You'll be left with a pi. and you'll be left with a pi here as well. On top of that, there's a cosine with a minus in it. And this is also another property that is important to know, is that if you have a cosine of a negative angle, it's basically equal to the cosine of the positive angle. They're equal to each other. This is a property from cosine. So knowing this and this, we could basically simplify this expression here. So let's see how it becomes. Essentially, because this is 2 pi, 2 and 2 cancel, so we get Vp over k pi. And cos of 0 is simply 1. This is 2 pi, the 2 and 2 cancels, the minus is gone, so we have k pi here. Here we also get 2 pi, and 2 and 2 is canceled, so it's k pi here. And we enter the minus so that I could get rid of this bracket. And also this is cos of 0, and cos of 0 is 1. But don't forget to add to distribute the minus inside the bracket. Therefore, those will be plus 1. So far, this is what we got. So we did a lot of steps here, and I tried to go very slowly so that you can see all the different steps that we've taken. Now, sometimes what people do is they go a bit faster, and I didn't want to do that. I wanted to really show you all the steps so you don't get lost anywhere here. But in reality, it's just a calculus problem here. We're just solving a pure calculus question, just an integration. Okay, so we're here. Are we done? Well, not quite. We can still clean up this and simplify it and make it a bit nicer. Okay, so let's do this on the next page. Okay, so now let's continue the analysis. So basically, what I did here is I simply took the last line that we left on the previous slide, and we'll just pick it up from here and continue. So this is what we have, and now it is interesting to do the following. We could basically combine the 1 and 1, and so that becomes 2, and then these two could be combined, and that becomes 2. And in fact, you could factor the 2 outside, so you'll have this. So you get this. And what this brings us is to an expression where you have 1 minus cosine of k pi. Now, don't forget what the k indices are. They're a summation, so they go from 1, 2, 3, 4, 5, all the way to large N, where N stands for the harmonics, the nth harmonic. Okay, so this is what we have now. If we have certain values for k, we'll get something, and if we have other kind of values, we'll get something else. So it really depends if it's even or odd. So I'm going to open a sidebar here, and I'll give you an explanation more in depth of how we could actually break this into odds and evens. So if your k is 1, 3, 5, 7, and so on, the answer will always be minus 1, right? So you could try it, and then you could kind of remember some of the trigonometry and that you've studied previously, and then you'll notice that the answer should be minus 1. Okay, because it's going to be on with a degree of 180 degrees. Okay, whereas if k is equal to 2, 4, 6, 8, and so on, the cosine will give you a 1, a positive 1. So this is what we get. Now, if you take this reality and you plug it here, so imagine if you have a minus 1, then you do 1 minus minus 1, so that becomes a 2, and that's fine. So if k are odds, this bracket here becomes a 2. However, if k are even, right, so if you use a k that is an even value, this will be 1 minus 1, which is 0. So this thing here, this entire thing will be 0 if you have k's that are even. It would only give you a value that is equal to 2, and therefore it's going to be 4 Vp k naught if it is odd. So let's just write it here, and this is essentially what you get. So if you have even, you'll get 0. If you have odd, you'll get this one here. And that's pretty much it. We found our bk. So we did the previous slide and this slide until we found some expression for bk. Now let's just bring it all together and write down our Fourier series. So I'm going to write the Fourier series. This is what we saw it is. And again, we said that it is this, not with the DC component, and not with AK, because it is an odd signal, not an even signal. So it's simply this. And now the only thing you need to do is, instead of BK, you enter this in here. So let's enter it in here. And this is what we do. So essentially, instead of BK, I enter 4V peak over K pi, and then the sinusoidal here with the different harmonics. But be careful, the summation will not go from 1, 2, and so on. It will only take indices that are odd, right? So 1, 3, 5, 7, and it goes all the way to the nth harmonic. The nth harmonic. And essentially, the nth harmonic should also be an odd value. This thing here, it should be an odd value. Now, one perhaps may want to make it a bit fancier, this expression. Usually when we have summations, we like to express them in continuous numbers. So 1, 2, 3, 4, 5, as opposed to numbers where some of them are jumped, like this one here, 1, 3, 5. We don't necessarily like to see it this way. So this step is really to make the expression a bit fancy. If you don't want to do this step, that's fine as well, but I just want to show it to you, just to show you the elegance of mathematics. So this is what we notice, is this. Instead of using indices 1, 3, 5, we rather have some indices 1, 2, 3, and let's just call it n instead of k. So how do we map from this to this? Well, we could simply use this relationship, right? So if this is something that is very generally, that is typically done when we do DSP, digital signal processing, we generally will have such things where we change the index so that it becomes more sequential, as opposed to having numbers that are skipped. Okay. So if you for instance enter 1 here, so it's going to be 2 times 1, that's going to be 2. 2 minus 1, that's 1. So that takes care of this. And if you enter 2, that becomes 4 minus 1, so that gives you a 3, and so on and so forth. So basically, instead of saying 1, 3, 5, we want to write it as 1, 2, 3, but we have to do this kind of mapping. So anywhere you see k, you can simply replace it by this expression here. Okay, and then the summation, you could simply run it from 1 all the way to the corresponding value for the harmonics. So this is essentially what we get. Now, what this means is that what we essentially did here is that we first of all took the constant part, the part that doesn't depend on k. So the 4, the v peak, and the pi. We could have also taken it here, put it here, and that's what we did. The 4, v peak, and pi, we took it outside the summation. Has no relationship with the indices of the summation. And instead of going from 1, 3, 5, we now change the index for the summation. We're going to use 1, 2, 3 all the way to a value. By the way, this is wrong. It shouldn't be n here. I just realized n is the harmonic, the maximum harmonic that we will use. So this should rather be n plus 1 divided by 2. N plus 1 divided by 2. So if this is odd, you add 1, it becomes even. You divide by 2, it should be an integer. So this is wrong. It should be n plus 1 divided by 2. Sorry about that. And that's it. So you, instead of k, we enter 2n minus 1, and instead of k here, we enter 2n minus 1. Again, I'm doing this just to make the expression more fancy. If you don't want to do this, you want to stick to this, that's fine as well. And that's fine. We could just live with it. So let's continue. And if you basically expand the summation, you could just expand it here, or you could expand it here. You could use whichever is nicer. This is perhaps easier to use when you want to expand. So you enter k equals to 1. You have 1 in the bottom, which is nothing. That's why I didn't write it. And you have the first harmonic. This is the second harmonic doesn't exist. We just take odd harmonics. So this is the third harmonic. We divide by 3. This is the fifth harmonic. Divide by 5. Seventh harmonic, and we divide by 7. And the outside is whatever the constant part that doesn't depend on k. So 4 v peak over pi, it's outside. Okay. So let's say somebody asks you, well, what is the voltage contribution of the fifth harmonic? Well, the voltage contribution of the fifth harmonic is, so this is where students do mistake. If somebody asks them, what is the voltage contribution of the fifth harmonic? They will say it's 1 over 5 volt. And this is wrong. You have to take this, you multiply it by 1 over 5. This is the voltage contribution of the fifth harmonic. The V peak, if you will, of the fifth harmonic. The peak voltage of the fifth harmonic is 4 V peak over 5 pi. That's what it is. Okay. So this is it. This gives us finally the answer that we want. So this picture here, this square wave signal, has the following Fourier series representation. Now that we have this, we pretty much have all that we need to represent this signal in the frequency domain. So it already our life is much simpler because we have this. So we struggle all the way just to get this. Now that we have this, we should be able to find the frequency domain of the signal right away. And I'll show you this on the next slide. Okay, so now we went through a somewhat lengthy analysis of a square waveform signal, and we were able to represent the signal in time domain based on a Fourier series. So essentially, we took the signal, this thing here, and we broke it down into an infinite series or a finite series, depending on when we decide to stop. But here we assumed it's like I put an equality now, and I put ... which means it's an infinite series. It will go on forever, and you will only look at the odd harmonics. So we got this, and we figure out this thing here through a lengthy analysis. And the analysis that we did is known as the Fourier series analysis. But if you look at this, we're still in the time domain, right? This is still S for the square wave signal in time domain. We're not in the frequency domain. And we told you that we're doing the Fourier series in order to look at the signal in the frequency domain. So how do we go from this to the frequency domain? Well, this almost gives you the frequency domain, right? So the frequency domain in reality is these coefficients. You remember these coefficients? So if we have, for instance, an odd signal, it's the BK coefficient in the Fourier series equation. That's your frequency domain. If we have an even signal, it's your A0 and AK coefficient. That gives you your frequency domain. So these coefficients are what we want. And where are these coefficients? They're here. They're this one here. This is just a constant, just a specific constant value times the different values here. So for instance, what is the voltage contribution of the third harmonic? Well, it's 4 Vp over 3 pi. What is the voltage contribution of the seventh harmonic? It's 4 Vp 7 pi, and so on and so forth. So these are the coefficients. This multiplied by the specific value that you see here, this gives us the BK coefficient. And this basically leads us to plot and to represent the signal, this signal in the frequency domain. And this is what we're after. So let's do it together. So here, like I said, we are still in the time domain, right? So it's t, but now we represented it in terms of harmonics, in terms of addition of sinusoidals. So we move it into the frequency domain. And to move it to frequency domain, we use Fs Fourier series. And so here we showed you Fs Fourier series in the time domain. Now let's show you how Fs Fourier series appears in the frequency domain. And this is how you can write it in the frequency domain. In this case, what you have is you have the magnitude, so we're doing voltages, so magnitude of voltages versus frequency. And this is your frequency domain representation. So here, these values that you see, these are the peak values of each sinusoidal. So again, if I ask you what is the peak value of a specific sinusoidal, it's simply 4 Vp over k pi. K is whichever one you're looking at. This is the peak value of each sinusoidal, not Vp. Vp is the peak value of the square wave. It is not the peak value of each sinusoidal. The peak value of each sinusoidal is this thing here, right? So you have to be careful here. This is where students do mistakes, right? Vp is not the peak value of the sinusoidal. Vp is the peak value of the square wave. The peak value of the of each sinusoidal is this thing here. Okay, and these spikes, if you will, they appear at discrete points, at f0, 2f0, at f0, not 2f0. 2f0 does not appear at 3f0, at 5f0, and so on and so forth. Only at odd multiples of the fundamental frequency. Anywhere else, at 2f0, at 4f0, or 6f0, 8f0, it's 0, right? So it's 0. Everywhere else, it's 0. Not only here, but also throughout the axis. Not only at these discrete points, but also beyond these integer values of k, it's also 0. Okay. Now, what if we want to see the frequency domain not in terms of voltages versus frequency? We want to see it in terms of dBm, like with a spectrum analyzer. How would we modify this? Well, this is straightforward. We could simply take the peak value, which is this thing here. We change it into the RMS value. The peak value, we change it into RMS value. And don't forget, you're doing the RMS not of a square wave. You want to find the RMS of a sinusoidal because you're looking at sinusoidals. The RMS value of each sinusoidal. So we change this peak value into a VRMS. From VRMS, then what we do is we determine the average power using Watt's law. From Watt's law, then we determine the dBW of the power of the signal. Once we have that, we apply Watt's law to determine the average value in dBW. And then after that, we change it into dBm. So there are 5 steps. You take the peak, you find the peak, which is this. You move from the peak to the RMS value. So you basically take this and you divide by square root of 2. Once you have it in the RMS value, then you use Watt's law to find the average power. So that's the 3rd step. Once you have the average power, then you do 10 log 10 of the value that you got, and that gives you the result in dBW. Once you have the value in dBW, then you add 30 to it, and the result will be in dBm. So there are 5 steps to move from a peak value to dBm. I hope that's clear. We've seen this in lecture 3 and earlier in this lecture. So we could do that, or if you want, you could use the fast track approach, where the fast track approach essentially is the formula that we derived in lecture 3, and we also used it earlier on in this lecture, where we do 20 log 10 of V peak, whatever V peak is. In this case, V peak is not this VP, it's this entire thing, right? So you want to find the V peak of each sinusoidal, which is this entire thing. So you enter it here, okay? Minus 10 log 10 Rn, where Rn is the internal resistance of the spectrum analyzer, plus 27. Why 27? Well, we derived it. We derived it in lecture 3. Go back to lecture 3 to see that. So you have both ways. Sometimes in an evaluation, I don't want you to spend too much time and so on, and perhaps you don't have this formula. You have to go through the 5 steps. It will take some time. I will tell you to plot the frequency domain in voltage versus frequency. Sometimes I will tell you to plot the frequency domain in dBm versus frequency. This is what you see with spectrum analyzer. This is what generally sometimes people do in books and in analysis, but it's not what you see in spectrum analyzer. Okay, so I hope that is clear. So let's use this. And let's consider maybe some values in order to plot the frequency domain. Let's consider the peak value of this square waveform. So a +1 here and -1 here. So the peak of the square waveform of 1 volt. And let's consider an internal impedance of the spectrum analyzer to be 50 ohms. And we said this is kind of reasonable with the spectrum analyzers that we typically use. Okay, so if we use that and we plug it in this expression, what do we get for the different values of odd harmonics? This is what you get, right? So at F naught, so you enter 4 times 1 divided by 1, because your K is 1 here, your K is 3, your K is 5, your K is 7. And then the internal resistance is 50, you add 25, and then you determine the value of dBm for each of the spikes. And this is how it looks like. Okay, so this thing here, this is the time domain representation of the square wave signal, which you will see with an oscilloscope, and this is the frequency domain representation of the square signal, a square waveform signal. So you see how the Fourier series is incredibly powerful. We had no idea how to determine the frequency response of it, or the frequency representation of it, and now we can. You know, it's all thanks to Joseph Fourier, right? The guy who came up with the Fourier series approach. Okay, and why do we do this? Well, this enables us to have an extra dimension in analyzing the signal. It enables us to figure out what is the bandwidth of the signal. If you look at this does not give you a clue on the bandwidth of the signal. This gives you a better understanding of the bandwidth of the signal. Okay. Now, one other thing that I would like to discuss before we wrap up with this slide is the following. Notice that I put 3 dots here, right? 3 dots. So you will have another spike where in 8F naught? No, you will have it in 9F naught, and in 11F naught, in 13F naught, only the odd numbers, right? Only odd numbers, 1, 3, 5, 7, 9, and so on. So only odd numbers. And the value of the power will diminish. If you see there is a specific pattern, the power of each spike, the voltage contribution for each of these different harmonics is actually diminishing. It's going down. But it will go on forever. These dots basically tells you that it will go on forever. In fact, I highlighted 3 things that leads you to believe that this will go on forever. Here we put equality, and we told you when you have equality, or when you have ... it means that it will go on forever. You will take all the harmonics until infinity. You will take all the harmonics until infinity. But if this is the case, then your bandwidth is equal to infinity. And this is not something that is practical in any way, shape, or form. We do not deal with infinite bandwidth. This is not something that is realistic, right? So if you say this to an actual engineer, they will laugh at you, right? This is not a realistic system. You need to have a finite bandwidth. So how do we ensure that this achieves a finite bandwidth? Well, one approach would be to, like we said, to not go until infinity, to stop at a specific large n. Remember we said this large n? Large n is the maximum, the highest value for the harmonics, right? So we stop at some value of the largest harmonic. Maybe we could say that this square waveform, I could approximate it with, I don't know, maybe 5 harmonics until the 5th harmonic. So we only take this, and then everything else we drop it, right? We notice that it's not significant, we just drop it. We represent this signal with only 3 spikes, and everything else we drop it. If we do this, we won't get exactly this, but we'll get pretty close to it. And this will not be an equality, it will be an approximation. Sometimes you want a higher precision, so maybe you'll add this harmonic as well, right? So you'll take until the 7th harmonic. Sometimes you have more, you have the capacity to take a bit more harmonics. Maybe you'll go until the I don't know, the 13th harmonic. But then beyond that, you don't find it to be useful, you drop it. So this is what we actually do in real life. And depending on when you stop, this is your bandwidth. So for instance, if I look at this and I stop at the 3rd harmonic, I stop here and I drop everything else, and I ask you, what is the bandwidth of your signal? The bandwidth is basically 3f naught. This is the bandwidth of the signal. Okay. So infinite bandwidth, that does not make any sense. So certainly, the larger we add harmonics, the better it will look in terms of this signal. It will look closer to what this signal is. But so this is one advantage of having a large number of harmonics, is that it will look more closer to the actual signal. But the key disadvantage is that the bandwidth will go to infinity. So this is where you have a trade-off. You want your signal, to the approximate signal with Fourier series, to resemble the actual signal, but you do not want to deal with infinite bandwidth. So this is where you apply a trade-off, and you say, well, I'm gonna stop at some level of harmonics, maybe the 5th, maybe the 7th, maybe the 9th, maybe the 11th, maybe the 13th, and I'm okay with the approximation. And also the bandwidth will be finite. So you get that. You won't get a perfect matching signal, but you'll get a finite bandwidth. And this is what we typically do in engineering, in telecommunication engineering. We cannot. It's not a perfect world. We cannot have. We cannot have everything that is working toward us, right? There are forces that can help us, and there are forces that cannot. And so therefore, we use something called the trade-off. It's somewhere in between where we benefit from what we have, and we try to make it as feasible as possible. Okay, I hope this makes sense. Otherwise, I'll try to explain a bit more on how we stop at a certain frequency when we talk about filters. In fact, when we say we drop all the other spikes, all the other these harmonics, and we only stop at the third harmonic, and how do we do that? Well, we use something called filters, and I'm sure you've seen filters in other courses, but now we're looking at it from a system level point of view, and we'll explain to you filters later on. Okay, on to the next slide. So just to recap, so far what we've seen is we've taken a periodic signal, and we said to ourselves, let's just consider the square wave signal. And we looked at the square wave signal, we got its general characteristics in the time domain. Then we represented this square wave signal using Fourier series techniques, and we were able to represent the square signals with an addition of multiple sinusoidals. And this was done in the time domain. Then we took that result and we looked at the Fourier series representation of the square wave signal in the frequency domain. Now that we moved to the frequency domain and we're able to see the square wave signal in the frequency domain, what are the key things that we could extract and see in the frequency domain? One big item and critical item that enables us that we're able to detect and to look at, to measure, and to assess is the bandwidth of a signal. The bandwidth of a signal is best seen and is best detected and is best understood at the frequency domain, not in the time domain. In fact, quite often the bandwidth cannot be detected in the time domain. You really have to move to the frequency domain to understand the bandwidth of a signal. Okay, and bandwidth is critical. So I'm sure you've saw bandwidth before in other courses. Maybe we've also talked about it in this course in different parts. But basically, very briefly, bandwidth of an information signal or bandwidth of a channel is the highest frequency that let's say your signal can have minus its lowest frequency that the signal can have. And this difference, this delta, is essentially the bandwidth of a signal. Okay, that's pretty much the definition of a bandwidth. And bandwidth the larger the bandwidth, the more information you could pack into the bandwidth. The smaller the bandwidth, in general, you could put less information into the bandwidth. Okay, that's kind of some basic understanding of bandwidth. And in fact, bandwidth and power, they always go hand in hand. You cannot just look at bandwidth by itself. You also have to say what is the power of the signal within that bandwidth. So they're always linked together. You cannot just say the bandwidth and not talk about its power. And you cannot just say power and not talk about its bandwidth. So they always go hand in hand. So so that being said, in fact, if you're interested, maybe I should mention this here, although it is kind of digressing from the topic. If you are interested to learn more about operating frequency, channel bandwidth, resource blocks, and so on, I have a good lengthy lecture on this in the wireless communication course. It's not part of this course, so you won't be evaluated on it per se, but you could, if you're curious, you could certainly look at that lecture. It's available on YouTube, and specifically I look at LTE, so 4G LTE as a case study when we look at operating frequency, channel bandwidth, resource blocks, and so on and so forth. So that's that. So let's see what we have here. So in here, what I show you is just essentially an image, and in this image we are approximating the square wave that we have. So this is your square wave signal, right? In here we just put in numbers, right? So we use the amplitude of 1 volt, the peak amplitude of 1 volt, and so that's 1 volt. This is V peak. So, and this is the minus V peak, so 1 volt, and also over a period of 1 second. Doesn't mean this is what we took. For us, this was T naught, and this was minus V peak. This is V peak, and each frequency is not an actual frequency. It was actually, well, it is an actual frequency, but it's not an actual number that we had in the example, in what I showed you before. It was more abstract. It was F naught, 3F naught, 5F naught, 7F naught, and so on and so forth. So if you see this, it essentially means F naught. So let's just consider that. What we will see here, that's that. Let's just link it to what the convention that we used on the previous slides. But now you have some numbers, so we were able to plot. So here you have your square wave signal. This is your original signal, and this is the estimate of it. So here we're estimating the square wave with only one sinusoidal, right? And you should get this by simply looking at the frequency domain. You notice that we are estimating this with one sinusoidal. This green thing here, if you look at it in the frequency domain, it's just one spike at F naught. One spike at F naught, and it has a certain voltage value, right? In the magnitude and voltage value, the peak value of the sinusoidal. Okay, so essentially this thing here simply represents the square wave signal, but we're only considering one sinusoidal, only one of them, right? That's why you only see this. And we said this is an infinite series. This is a series that goes on. You could take more sinusoidals, but here we only took one. So just by looking at this, let's see what can we characterize. So if, let's say, we ask you how many harmonics did you use here? Well, the answer is you only used one of them. If you see one spike, it means you only use one of them. You see one spike here, it means you only use one of them. The other question is, what is the largest harmonic? What is the largest? So N, remember N, we said is the largest harmonic that you can have. In the summation, we said there's a summation. K goes from 1, 3, 5, 7, all the way to large N. This is what it is, right? So it's the value that you have here. And essentially the largest harmonic is 1. Okay, so now the next question is, we said that when we look at the frequency domain of a signal, essentially of course we were able to move to the frequency domain using the Fourier series. We said that the Fourier series is useful to determine the bandwidth of a periodic signal. Right? So we said that, and we have the Fourier series. Well, how do you see the bandwidth here? Well, for the bandwidth, essentially is if this is F naught, you go from the axis here from 0 to F naught, and you do the delta here. And essentially this means that the bandwidth of this signal is F naught. That's essentially what it means. Okay? Now, let's move on to a next one. Let's now consider not just two harmonics, but let's consider not just one harmonic, but let's consider two harmonics. Right? Let's consider two harmonics. So if you see here, you see two spikes because we're considering two harmonics. This is the first harmonic related to the fundamental frequency. And this is so this is F naught, 2F naught, and this is the third harmonic here related to this. In terms of the size, this is a third of this one, right? A third of this one. And the amplitude of this one is V peak over pi. The amplitude of this one is V peak over 3 pi, okay? The peak amplitude. So now we're considering true harmonics. So if we ask you, how many harmonics are you using? Well, we're using 1 plus 1, that's 2. What is the largest harmonic? The largest harmonic that you're using is 3. So maybe you should be careful with the naming conventions. This is referred to as the first harmonic. This is referred to as the third harmonic. But if we tell you how many harmonics you're using in your estimate, you're using 2. So that's the convention. You should distinguish between these two. They are not the same. This is the largest harmonic, which is the value that you see here. And this is the number of harmonics. How many spikes do you see? Well, you only see 2. That's why we put 2 here. And you also see the number of harmonics in the peaks here. So you're estimating. Your estimate is better than 1 harmonic. It's a bit better. And you notice you see 2 peaks here. 1 peak and another peak. And if we ask you, well, what is the bandwidth of this signal with this estimate with 2 harmonics? The bandwidth is this value here, which is 3F naught minus 0. And therefore, the bandwidth is 3F naught. Okay, so let's see what happens if we improve this a bit more. We improve the estimation, right? So we try to estimate this a bit better. So if we add an extra term, what happens? So let's look at this and let's see the changes. So now we are suddenly adding a third harmonic. So now the question is, how many harmonics do you have? You have 1, 2, 3 harmonics. What is the largest harmonic? It's 5. What is the bandwidth? This is 5F naught. So 5F naught minus 0. This delta here, this difference here, this is your bandwidth. And if you look at the estimate, it's already shaping up to look much nicer. The estimation is becoming quite good. It looks quite closer to the square signal. Remember when we only had this one here? It was very bad. It was just a sinusoidal. It did overlap, but not quite. Now with 3 harmonics, it's shaping up quite well. It looks much better. Okay, and you could also notice these 3 peaks, 1, 2, 3, which means that you have 3 harmonics. That's also another way of looking at it. Okay, if we can, maybe we'll add a 4th harmonic and let's see the improvement. So you are kind of seeing that the more harmonics you add, the match between the estimate, this green line, and the actual signal, the red line, is becoming closer. They're becoming more, they're matching quite well, right? So that's what we expect. So let's see what happens. So let's add another harmonic. So now we added the 7 and here, the 7 omega naught. And if we count how many harmonics we have 1, 2, 3, 4. That's why you have 4. If you don't want to count here, you could also count the peaks that you have in the estimate in the time domain. 1, 2, 3, 4. That's also 4 as well. If you don't want to do that, you could look at it in the frequency domain, and you could also see your 4 harmonics. 1, 2, 3, 4. So this 4, we're detecting it in different places. In this representation, 1, 2, 3, 4. In here, 1, 2, 3, 4. And also in the peaks in the time domain, 1, 2, 3, 4. And that's why we have 4 harmonics. What is the largest harmonic? Well, the largest harmonic that we consider so far is 7 omega naught. So we have the 7th harmonic. So big N is 7. And what is the bandwidth? Well, the bandwidth is 7 F naught. So 7 omega naught or 7 F naught. This is the bandwidth that we have. So as we include more harmonics, the approximation improves, but the bandwidth also increases. So there's that we consider. Okay, maybe we increase one more time just to see what happens. And we have this. And of course here as well, we added another harmonic. And now the estimate is becoming even better than what it was before. The more harmonics we add, the closer you become to the original signal. Okay, there's still these kind of ripples, but that's okay right? You cannot get rid of them. In fact, you might need to add maybe 50 of them, maybe 40 of them to gradually get rid of these ripples, right? But as you add more, the bandwidth increases. In reality, in communication, we don't want the bandwidth to increase. This is not a good thing, right? So we want to in reality, in telecommunication, we want to convey as much information as possible about a signal with as little bandwidth as possible, right? So increasing the bandwidth is not something that is desired. So we want to do that. Sometimes we could say also increasing the bandwidth increases the speed. In that sense, yes, we want that. But from a resource point of view, you want to have less bandwidth. We want to use less bandwidth to convey more information. And there are many reasons why we want to do that, but one key reason why one would want to do that is in order to enable multiple users to use the same channel. And so if you're using a wire, you want to have multiple parallel users to have access to the same resource. So if your bandwidth uses a lot, is large for one user, then you're just kind of, the channel is only occupied by you and nobody else can use it. And this is not a good thing. Right, so bandwidth is, you can think of bandwidth as a finite resource, and you can think of bandwidth as money, and therefore you want to use it very smartly. And therefore, like I said, in communications, we want to convey as much information in a signal as possible with as little bandwidth as possible. And that's very critical. Okay, so let's see here. How many do we have? We have 1, 2, 3, 4, 5. So we have 5 harmonics. We could also see it here. 1, 2, 3, 4, 5. We could also see it here. 1, 2, 3, 4, 5. Okay. What else do we have? What is the largest harmonic? Well, the largest harmonic is 9. And what is the bandwidth here? This point here is 9 f naught minus 0, and therefore the bandwidth is 9 f naught. Okay. So this is what we're able to see. So I guess one big conclusion that we get from this is we like to have more harmonics. It will give us a good estimate of the original signal, but we should be careful about it. We don't want this to be very, very big. We want to have this smaller, because this is a finite resource and we want to use it smartly so that multiple users can use a certain medium, a certain wire, a certain channel in a smart way. So I did here a small tree where this is what I've written. Increasing the number of harmonics. So if we increase the number of harmonics, or if we could also say increasing the number of n, right? They're kind of they're not equal, but they go hand in hand, right? They're proportional to each other. If you increase the number of harmonics, the number of n also is increasing. So you could say both of them. What are the advantages of this, and what are the disadvantages of this? So the key advantage, like I mentioned to you in here, is that the Fourier series signal representation will closely match the original signal. It will closely match to it. Still some ripples. You could get rid of the ripples as you increase even more so with harmonics, maybe up to 40, up to 50, but it will closely match the original signal. You will have less distortion as you increase the number of harmonics, or as you increase the number of n. So that's a good thing. At the same time, we said that there is a disadvantage, because as you increase n, the bandwidth increases, and you do not want a large bandwidth. Certainly, we said if we use it in a mathematical sense, you'll have an infinite bandwidth, but this doesn't make any sense from a physical point of view. You don't have any medium, a wire, or a channel that has infinite bandwidth. It simply does not exist. We live in real world, and we live in a physical real world. In a physical real world, everything is finite and it has a certain capacity. So this is not possible. You want to have a finite value, and this finite value, you want it to be as small as possible. So more bandwidth will be needed to transmit the signal, and this is not good. So now you need to find a compromise. How do you have less distortion, but also have a smaller bandwidth? And this will require some trade-off and some skills from an engineering point of view. And this is what engineers are good at, is to find this, right? So to perhaps decide on a specific number of harmonics And also these number of harmonics will ensure a lower number of a lower size for the bandwidth. Okay, so I hope this is a clear slide. So I wanted to add more information to the previous slide. Therefore, I created this slide so that hopefully you get a better understanding of what's going on. So let's move on to the next slide. In this slide, my objective is to kind of explain the whole idea of what happens if we shift the waveform, this waveform that we have, this periodic waveform that we have, whatever the case might be. In this case, we have a square waveform, but whatever the case might be, if we shifted on the axis, on the amplitude axis, the voltage axis, this thing here, if we move it here, what happens to the various characteristics of the signal? What do we observe? In general, just very briefly, this is known as the DC offset. So the signal will have something referred to as a DC offset. It will either include the DC component or not include the DC component. And we want to see how this is actually impacted, and that's the objective of this slide. So here what I did is I brought back the same waveform that we used throughout this lecture, this square waveform, and this is the way we analyzed it throughout this lecture. It has a lower level of minus VP, a higher level of VP. It has a certain period, a period T naught. I did not include it here, but a period T naught. And we're in the time domain, and the values that you have here, these are in voltages. Okay, time domain. Now, we also determined that after some lengthy analysis, we were able to represent this signal in terms of its frequency series equivalent, right? So it's a series, and it has a bunch of sinusoidals, and it goes on, and this is what we got. We were also able to show this signal in the frequency domain, and this is what we got. Now, we could have just showed it in a generic way with no specific values, just a picture, but here we use a specific value in order to make it very concrete on how to get these different power levels, and we explain to you how to get it. In this case, we use these two numbers for the internal resistance of the spectrum analyzer and a very simple V peak of 1 volt, just to show you how we got this. Now, at this point, my interest is to kind of look at the signal again. This is what we have, same signal again. But what if we move it? What if we shift it somehow? Okay, so let's look at what we mean. So we take the signal and we shift it. We shift it. In this case, we shifted it by a value of VP. We were here and we brought it up. So essentially every single part of the waveform went up by a value of VP. We added basically a DC component of VP. It doesn't have to be VP. It could be any voltage that we want. But in this case, we did VP. And now what it means is that this level here will be a 0 volt. This level here will become 2 VP. And we want to know what is the impact that we will have on the signal in this case. The short answer is you simply added, to whatever signal you had, you simply added a DC component of VP. So basically, the way you would get this would be simply to rewrite this and add VP component to it. Okay, so let's do that. And this is essentially what you get. This is what you get. You see here, this is the component that we added. Before, if you remove this, you're back to the picture that we have here with this expression. But because of the offset, DC offset, this is how it looks like. Okay. Like mentioned to you, this is referred to as the DC component of the signal. So now if you look at the signal, right away, you know it has a DC component. By the way, a DC component could also be detected right away visually by simply looking at the graph. So if I look at the graph, this is a graph, and if I look at it, by the way, if a signal is using the trick of knowing if a signal is even or odd, is always good to determine if there is a DC component. So here, I know the signal is odd, so certainly it will not have a DC component. But here, if you look at this signal, and then you ask yourself, is this signal an even or odd signal? Well, this signal is neither even, neither odd. right? If it was an even signal, whatever you have on this side should have a mirror image on the other side. So that's not the case. So we know it's not even. Is it an odd signal? It's not an odd signal because it doesn't have a symmetry with respect to the origin. So this is not an even signal. This is not an odd signal. Okay, so just something that you should realize. Because of the offset, it's no longer like this. This, however, is an odd signal. Right away, you can see that it is an odd signal. Okay, so let's continue with the analysis. What happens now in the frequency domain? So in the frequency domain, this is what happens. We use the principle of linearity, and essentially what linearity tells you is that, we saw this earlier in this lecture, when we invoke the linearity principle of Fourier series, we're basically adding two signals. We're adding a DC signal, just a flat line, a flat DC power, a flat DC voltage across different times of VP, plus the original signal. And therefore, in the frequency domain, we simply add the spike for this. So when you have a flat DC component, what happens to it in the frequency domain is just the spike of the power of this signal, just the spike of it at frequency 0. That's frequency 0, right? So frequency 0 is where you have your DC component. So, and we put it here, and in fact, the value with the corresponding numbers is 13 dBm. This is what you get. This is your DC component here. So we moved it. We see the DC component in the equation. We simply add it. We see the DC component in the frequency domain. We simply add a spike at frequency 0. And you need to figure out what is this value. Now, this value, you have to be careful. It is not like what we did before. This is a DC component. Remember when we got the power for the others? We went through 5 steps, right? So step 1 was to determine the peak value of each sinusoidal. Step 2 was to find the RMS value of each of these peak values. Step 3 was to determine the average power. Step 4 was to find dBW. And step 5 was to find dBm, which is by simply adding 30. And we got this formula that we derived in lecture 3, which is 20 log 10 of Vp minus 10 log 10 of input resistance plus 27. You cannot use this equation for the DC component. It will not work. And the key reason why it will not work is that that equation has an RMS. We determine the RMS value. In here, in the DC component, you do not need to find the RMS value. In fact, the RMS value and the actual value here, it will be the same. So you cannot use that equation. And so doing a V peak divided by square root of 2, this would not work here. You do not need to do that. It is already in the DC form. So you do not need to find its RMS value. So in reality, to find this, you have to go through now 4 steps, not 5 steps like we did for the others. For the DC component, you have to go into 4 steps. You find the actual offset, the DC offset, this thing here, whatever the value might be. In this case, we use VP. Sometimes I could simply use, I don't know, 0.2 or 0.3, whatever you get in your situation or in a certain evaluation, use that. In this case, we gave you VP. It just happens that that's the case, but it could be anything. Whatever the offset is, the voltage, you simply have to find its average power. And the way to find the average power is you simply use Watt's law. And we know Watt's law from electrical fundamentals. There's 3 ways to see Watt's law. V times I squared times R, or V squared divided by R. And the one that makes more sense for us is to use V squared divided by R because we have the internal resistance of the spectrum analyzer. So you find the average power. So essentially you take this voltage, you square it, you divide by the internal resistance of the spectrum analyzer. If it's not given to you, assume a 50 ohm. Then you change this value to dBW. So basically you do 10 log 10 of the power that you got, the average power that you got. And then the result that you get, you add 30 to it. So if you do this on paper and you clean it up a bit, basically you'll have something like this. This is the result that you get. So anytime you deal with a DC value and you want to show it in dBm, this is essentially the equation that you have to use, not the other one. And in fact, you will need to show this. I didn't have time or to show it here in space to show it on this slide, so I'm going to just show you the result. So it is 20 log 10 VDC, whatever it is. So in this case, our VDC is this thing here. So we would enter this minus 10 log 10 RN plus 30. Notice it's no longer plus 27. Plus 27 was for these ones. This is plus 30. And it's increased by 3 dBs because we don't do the square root of 2. Right? Remember, we had the square root of 2 for sinusoidals. Here we don't have this. We don't do the RMS. Okay. So just be very careful with this. Sometimes even I notice this mistakes even in some books. So they do the mistake of not doing determining the DC component correctly. Okay, that's pretty much it. So these are kind of the big things that I wanted to mention on this slide. So if we were to recap very quickly, how are the different ways of determining if there is a DC offset in a signal? So I was thinking about this earlier today. There are basically 5 ways that you can detect the DC offset in a signal. 5 ways. There are 2 ways that you could detect that analytically, and there are 3 ways that you could detect that visually by looking and inspecting a signal. Analytically, one way to do this is to simply use the Fourier series expansion, right? So basically, you know the formula. So Fourier series is A0 divided by 2 plus the summation of AK cosine of the generic harmonics plus BK sine of the generic harmonics, and then you go through the analysis, and if you get anything for A0, that's your DC component. So you could use the Fourier series analysis. That's one approach, but this is a very, very long and tedious approach. Imagine because of the offset, we had to go back and redo all this and derive it. It would be very, very long. So not necessarily the recommended approach, but nonetheless, it is there. So it's to use the Fourier series equation. Like I said, it's not recommended to do it. It would be like a pure nightmare to re-derive all this, whereas here we just notice it through common sense. But you can still do it nonetheless. The other approach that you could do is you could use the linearity principle of Fourier series. Essentially, what you say to yourself is, I have this signal. I add another signal that is only flat, across all times with a certain voltage value. And then when I move it to the frequency domain, the linearity will stay the same. So I look at the Fourier series of the flat one, which is only a spike at frequency 0, and I add it to the other spikes that I got for this one. And that's what we do with linearity. So that's the second analytical approach, is to use the linearity property of Fourier series. The third approach essentially would be to look at your signal and then to detect whether you have a DC offset or not. You could look at your signal and you could say, is my signal even? Is my signal odd? If your signal is even, then it means you may have a DC component or you may not have a DC component. It depends, right? So not necessarily because you have an even signal that you have one. But at least you know for sure that it's either you have it or you don't. If you, on the other hand, your signal is odd, like this one here, you know for a fact that there is no DC component. If you have a signal like this, it's neither odd or even, then there is a big likelihood that there is a DC component. Okay, so in fact, the DC component is very probable. Okay, so when it's the only case where you know for sure there is no DC component is when the signal, when you look at it in the time domain, is odd. You know for a fact there is no DC component. All the other cases, it is possible to have a DC component. Okay, it doesn't mean it's always there, but it is possible. So there are cases where you have an even signal and there is no DC component. So you really have to inspect it to see that. But that gives you another hint of visualizing DC in the time domain. A fourth way to know if you have a DC component is to look at the average. So basically, you look at a figure you have your figure, and then you simply average it just by looking at it. You say, okay, so my signal goes from minus VP to VP, and it goes up and down. So if I look at the average, what is the average voltage? Well, the average voltage is 0. So I know my DC component is 0. Okay, so that's one very quick way to detect the DC component. You look at this one here. You say, okay, fine. So I have the square wave signal. It goes between 0 to 2 VP. Okay, that looks fine. But what is the average value? If I were to average this waveform, this waveform that goes up and down, well, the average will be in the middle. And the middle is between 0 and 2 VP, which is basically VP. And that's the average. So averaging your signal in the time domain by simply looking at it is also another trick of getting the DC component very quickly. So that's a fourth way. The fifth way of knowing if you have a DC component, and let's say for some reason somebody gave you the frequency response, or the frequency, they display to you the frequency of the signal, is to look at frequency 0. You look at frequency 0. Do you have any spike? Well, frequency is 0, there is no spike, no DC component. At frequency 0, there is a spike, well, there is a DC component. Right? So now I really showed you 5 ways of detecting DC. First way is to apply Fourier series equation. Not recommended because it's too long, but it's still there. The second way is to apply linearity. These are 2 analytical ways. The third way is to ask yourself, is it odd or even? The fourth way is to look to determine the average of the signal by simply inspecting the time domain. The fifth way is to look at the frequency domain and look at frequency 0 and noticing if there is a spike or not. These are 5 ways to quickly determine if your signal has a DC component. So I hope that's understandable. Let's move on to the next slide. On the previous slide, we saw the impact of the DC offset. Basically, we learned the impact that a DC offset has on the frequency domain of a signal. So we realized that essentially you'll just end up having the signal as it was before, except now you will have a spike at frequency 0. It's just DC, so there's no frequency, and therefore you'll have a spike at frequency 0. And we figure out how to actually assess the value of this DC component. At this point, we ask ourselves, well, what if now we want to shift in the time domain? Well, we're still in the time domain, and both of them were in the time domain, but over there we shifted on the amplitude. Right, so we shifted in the amplitude here. Now we want to know if we shift the figure or the signal here, like this, horizontally. Over there, we shifted vertically with a DC offset. Here, with the time shift, we want to shift it horizontally. What is the impact that this may have on the signal at the frequency domain? What happens at the frequency domain? I'm sure something happens, but what happens? So that's the question that we're asking here. And let's just try to figure out together what happens. We'll just do it in this slides. So what I'm going to do here is I again brought the same signal that we analyzed throughout this lecture. Just put it here. Again, it's a square wave signal, and it has a lower value of minus VP, upper value of VP, and a period of T naught. Okay. So let's go on with the analysis. Before we continue, I just rewrote what we determined, right? So we applied Fourier series, and we wrote the Fourier series in a nice, elegant, compact representation here. And I showed you how we derived this. You can see slide 6. In fact, as I mentioned in slide 6, there was a mistake here in the on the upper for the summation. It should be n plus 1 divided by 2. So on slide 6, this wasn't done. I corrected it here. So this is what you're supposed to see, where n is in fact the largest harmonic. But we did some mapping, and that's why it should be like this. And all of this is explained in slide 6. So anyways, if you don't like this, we essentially got this, right? So either this or this, they both mean the same. But I brought it here because we'll use this in the analysis that we'll do on this slide. Okay, so this thing is really related to this this image here, this signal that you see here. And we did this earlier in this lecture. Now we ask ourselves about time shift. Time shift, like I told you, is related to shifting the signal horizontally. If you do s of t minus t naught, it means that you are shifting the signal to the right. So when you have minus t naught, you're shifting the signal to the right by t naught, whatever it is, 5 seconds, 5 milliseconds, 10, 12, 1.3 milliseconds, 1.3 seconds, whatever it is. We don't know what it is. It's just a generic identifier here. But anytime you see a minus, it means the signal is shifted to the right. Anytime you see a plus, right? So you have a plus, t plus t naught, it means the signal is shifted backward. It's shifted this way. It's shifted to the negative side of the t-axis. Okay, so it is kind of counterintuitive, right? So st plus t naught, the signal will be shifted to the left toward the negative side of the t-axis. St minus t naught, the signal will be shifted to the right by a value of t naught. Okay. By the way, these are not the same thing. This is big T naught. This is just some generic T naught, small T naught. They're not necessarily the same. Okay, so this is referred to as time shift, right? So maybe you've seen this in other courses. I'm not sure, but this is something that we see a lot in communications and also in signal processing. Let's continue. Now that we know what time shift is, let's continue. So I want to show you the shift. Did you see the shift? We shifted the figure by a value of t naught divided by 4, right? So we shifted it by a value of t naught divided by 4, by this much, right? By a value of t naught divided by 4, we just moved it, okay? And the period doesn't change. The signal is still, it has the same period. And the period is this. We could just look at it here. You could look at whichever period you prefer, but let's just keep looking at it around the origin, which is this. The only major difference that you see here is that earlier in the signal that we analyzed, all that we have analyzed was with a square wave that was an odd signal. Now that we have shifted the signal and you look at this signal is no longer odd. This signal is an even signal, right? So it's an even signal, and that's it. So that's a major characteristic that you see by looking at a signal that is like this. So that's great. We knew, for instance, that when we had an odd signal, there was no way to have a DC component, like we said earlier. But now that it became an even signal, it is possible to have a DC component. A DC component is possible. Does it mean for sure you're going to have one? No, not necessarily, but it is possible. Now, so what would you do to find a DC component? Well, you could just look at the average. The average is 0, so we know still, although now it's an even signal, it still does not have a DC component. Or what you could do is you could measure this area, this area, this area, and this area. And by doing that, you'll realize that this is a positive area, this is a positive area, this is a negative area, this is a negative area. You add them together, it is 0, and therefore the average around the period is 0, and therefore you have no DC component. So that's just related to the previous slide, but I still wanted to mention it here. So let's continue. Let's ask ourselves, how on earth can we find a representation like this? So basically a Fourier series expansion in the time domain for this figure. Now, you might say, well, let's just go back and use the Fourier series equations. That's a possibility, but in fact, it might not necessarily be the smartest approach. What you could do is basically just reuse what you found earlier. You found this signal. Now what you are doing is you simply shifted it to the left, toward the negative time axis by a value of t naught divided by 4. So what you would write is you would write s squared, so this thing here, but instead of t, you put t plus t naught over 4, which means that you shifted it to the not to the right. Did I say, if I said to the right? I'm sorry. We shifted it to the left, toward the negative side, to the left by t over 4. That's why we have a plus here. So when you see a plus, it means the wave was shifted to the left by t over 4. So we enter this. And that's it. The rest is just about arithmetics and math. So what basically means is that anywhere you see in this equation a t, simply replace it by t plus t naught over 4. So let's do that. Let's do that together. So here, again, we're putting an approximation because we're stopping at a specific harmonic value. That's why we put an approximation. If on the other hand this was an infinity, then we put an equality here. It means we take all the harmonics, but we're engineers. We don't do silly mathematics. That doesn't mean much for us. We want practical systems, and therefore we put an actual definite value of harmonic. And that's why we have this big N, and that's why you have an approximation here. So it's kind of a repeat of what I said earlier. So we just rewrite it again. We rewrite this expression. The only difference is instead of entering T here, we enter T plus T big T naught over 4. Okay, we enter it here in this equation, and then the rest we have this. Now, if you don't like this, you could in fact just do this approach in this here, and then kind of derive it that way. But I like to do it using the main one, the compact representation. I think it's more scientific, and it gives us a better view of how the expansion for this wave will be. So let's just do that. But if you don't like it, then you can straight away enter T plus T naught over 4 to this one here, and then you could do some manipulations to simplify it. But I'm going to do it on the main one, on the summation one. So let's proceed. Here I said let's look at the sidebar to kind of simplify this. Let's open a sidebar and just look at it there. So let's do that. So I just rewrote this here. Rewrote it here. The next step, what we will do is we will distribute this to each component. The 2n minus 1 omega naught to the t, and the 2n minus 1 omega naught to the big T over 4. So we'll just put it to each of the components. Basically, we'll just going through the process of the multiplication inside a sinusoidal. So we do this. We get 2n minus 1 omega naught t plus 2n minus 1 times omega naught t naught over 4. At some point earlier in this lecture, we said that anytime you see an omega naught multiplied by the period, this is essentially equal to 2 pi. So you could right away remove this and enter 2 pi. That's a better, it gives us a more direct result. So let's just do that. Let's do that. And what we end up getting is this. So what do we get? We get this expression here, which is sine of this part. So I just rewrote it again. And let's give it an identifier, sine, let's call it A for now. And this part here, 2 pi. So 2 divided by 4, that becomes pi over 2. So we have 2n minus 1 times pi over 2. And let's call this thing here B. Let's just call them A and B. So we know we have this identity in trigonometry that if you have a sinusoidal of A plus B, it is equal to the sine of A times cosine of B plus cosine of A times sine of B. So I'm sure you've seen this somewhere in the different math courses that you've taken. Okay, so this is just basic trigonometry. And so we just do this conversion. So I'm going to rewrite it, but instead of A and B, I'm going to just put in the actual values. So I'll just rewrite it, put in the actual values. So sine of this, I just put it in. Cosine of this thing here, put it in. Plus cosine of A, put it in. Multiplied by sine of B, we put it in. Now, if you notice here, 2n minus 1. 2n minus 1, this, if you try it for the different values of 1, 2, 3, 4, this basically will be a sequence of odd numbers. So it would either be 1, 3, 5, and so on. So any different multiples so odd multiples of pi over 2 will, with a cosine, will always be a 0. So you could try it on your own, but any odd multiples of pi over 2 for a cosine will always be 0. This is just basics of trigonometry. So this will be 0. If this is 0 multiplied by this, all this will go away. So that's gone. And we're left with this and with this thing here. Now, this thing here, again, these are 2n minus 1. These are just the sequence of numbers. So if you enter 1, 2, 3, 4, 5, and then you try it in the 2n minus 1, you'll end up getting just a sequence of odd numbers. 1, 3,
5, 7, 9, 11, 13, and so on and so forth, just odd numbers, right? And we did the mapping in slide 6. This is why we're using this 2n minus 1. I explained it over there. You can listen to slide 6 again to see why we got it this way. So if you have these odd multiples of pi over 2, some of them will give you a plus 1, and some of them will give you a minus 1. In fact, in this sequence, in terms of n's, in terms of n, not in terms of 2n minus 1 or k as we used to call it before, it means that anytime you have a 1, n equals 1, n equals to 3, and so on and so forth, the result should be a positive 1. And anytime you have an even number, like n equals to 2, n equals to 4, this will essentially give you a negative result. So we could essentially just write it in a fancy way as such, which is minus 1. So this thing here, we could just write minus 1 to the power of n plus 1. So if you have 1, 3, 5, and so on, this will become an even number, and this will become positive. And if you have results that are odd, let's say 3, 5, 7, this becomes negative, right? So if let's say you have, if you have n's that are even numbers like 2, 4, 6, this becomes an odd number, and the negative will remain, and that's kind of takes care of this. So it's just a fancy way of getting rid of this and writing it in a more compact way. As for the rest, we just rewrite it, and this part here will be 0. By the way, instead of doing n plus 1, you could have also done n minus 1. I just decided to do it n plus 1. It just seems nicer to have a positive instead of a negative. So that's why I put this. But if you do n minus 1, it would still work as well. So anyways, we do all this in this sidebar. This thing here, now we could just plug it back again. Instead of this sidebar, I could just plug in this value here. And then the rest is just I enter it as is. And I could just try it for different values of n. And this is what we get. So we got the sequence. This is what we got. Okay. And again, I told you, if you don't like all this analysis and this sophisticated way of doing it, some might say, you could just directly do this t plus t naught over 4 to this, right? To each of them. It might be a bit longer because you have to do it for each one of them. But if that's what you like, then that's fine. But otherwise, if you prefer the more sophisticated way of doing it, well, I explain it here. Okay, so this is essentially the result that we got. So just by inspecting it, are we kind of okay with the result? Well, I mean, if we look at the result has a bunch of cosines, right? And do we expect to see cosines in the Fourier series? We actually do expect to see cosines, because this thing here right now is no longer an odd signal. This is an even signal. And we said earlier on, maybe at the beginning of the lecture, anytime you work with a Fourier series and you have an even signal, you will have a bunch of cosines, not a bunch of sines, right? Because even signals are related to cosines. So that's a good sign. We also said that it is possible to have a DC offset, an A naught, but here there is no A naught. The A naught is 0, and that's fine. So there is no A naught, there is no DC component. So this is what we got. Now, if you look at this, there's also so it's kind of looked similar to the one without the time shifting, right? Without the time shifting. If you look at it, they kind of look the same. The multiple here is the same. The values that you have in front of each sinusoidal is the same. The key difference is that these ones are sine, these ones are cosine. That's a key difference. The other key difference is that this is all plus everywhere. Here you have plus, minus, and it keeps alternating, plus, minus, and so on and so forth. So does that impact us for the frequency domain? Well, it turns out it doesn't. This is the important result that you should realize, is that time shifting has no impact on the frequency domain, especially since we're looking at the frequency domain at the magnitude, right? So if you don't look at it at the magnitude and you take into account the impact of phase, then sure, this shifting will have an impact. But for us,
we are practical people. We want to understand it the way that a spectrum analyzer does it. In a spectrum analyzer, phase has no role to play, and therefore we only look at it from a magnitude point of view. So from a magnitude point of view, any shifting you do on the time domain will not change your frequency domain. It has no impact. So shift it whichever way you want. It doesn't have to be T0/4. Shift it more to the left, more to the right. Does not matter. Do whatever you want to do in terms of shifting. It will not change your frequency domain. It will be exactly the same thing as this one here. It will be the same as what we got earlier throughout this lecture. It will not change. And this is a remarkable result because, again, we are looking at the magnitude, right? We're looking at the magnitude. And what magnitude is essentially, so if I ask you, what is the magnitude, what is the V peak of this thing here, the 7th harmonic for this one here? Some students will tell me, well, it's minus 1/7 volts. Well, the answer is wrong. We said magnitude, so you cannot have a minus. Also, it's wrong because you forgot to multiply by this. So the actual answer to the magnitude of this harmonic is 4 VP over 7 pi. And there is no minus because we take the absolute value. We're looking at the magnitude. So that's your V peak for this one. And then for the rest, you just go through the steps, the 5 steps, in order to find the P, the power in dBm, or you could just use the formula with the plus 27 in it at the end, right? So you could use that here. So at the end, what I'm trying to tell you is that shifting anywhere on the time domain has no influence on the frequency domain when you look at it with respect to magnitude and to frequency. So that's the key thing that is remarkable to realize on this slide, and that's it. Now again, we did all this, and again, some might say, well, why don't we just use Fourier series to derive all this? And you could try it with Fourier series. You'll go through the same nightmare that we went through earlier in this slide, and it will take forever. But doing it straight with the shifting of the result that we got earlier is much easier. And so if you don't trust me, you could try the Fourier series, and you'll see that doing the shifting is way faster to get to this result here, which is interesting. Okay, so let's move on to the next slide. Finally, we arrived to the last slide that I'd like to show you in this lecture, which is the Fourier series expansion and the time domain for the various signals. And of course, when you have the Fourier series expansion in the time domain, you could right away jump in to the frequency domain, irrespective of the sinusoidal. If it's sine or cosine, it will be the same thing. Does not matter. You simply look at which harmonic it happened, and then you just put a spike in the frequency domain. And we showed this in lecture 3, but this also applies here throughout this lecture. Okay, so one of the ones that I'd like to show you, and I just showed it to you on the last slide, which is a square wave, but not the square wave that we saw before. This is a square wave that is even, right? That's why I put between bracket even. So it looks like this, and we in fact just derived it, but this is how the equation is for this expression. It looks quite similar to the one where it's a square wave that is odd, except instead of cosine, it's sine, and we don't alternate between minus and plus, right? We don't alternate there. The amplitude is the same. Everything else is the same. The harmonics is still the same. So the frequency domain of this will be exactly the same as the square wave that is odd that we derived earlier in the lecture. And like we said, if you look at, for instance, if I ask you what is the frequency domain of this harmonic, well, you simply say that it is the V peak, so 4 VP over 5 pi. That's the peak voltage of this harmonic, and there's a spike of this value at 5 F0, right? And so it's the same thing whether you have a sine or a cosine. We said sine or cosine does not matter in the frequency domain, right? We talked about it in lecture 3. So this is the result that we got, and in fact, we also showed it on the previous slide. Well, the key remarkable thing that we could observe here is that only the odd harmonics are relevant. So this is true for both square wave that is odd and square wave that is even. Only the odd harmonics are relevant. Even harmonics, we don't care about that. Okay, they have no impact in the signal. even harmonics, they simply have no impact in anything that has to do with a periodic square wave. Okay, the other signal that I'd like to show you is the triangular wave, right? So triangular wave, we're not going to derive it. It will take forever, but I'll just show you the result. So again, it looks like this. It's periodic, it has a period T naught, and that's what a triangular wave is. And so if we do the expansion, this is how it would look like. Right? This is how it would look like. You have to show it. It will be long, it will be tedious, but this is how it would look like. Again, we see here, similar to this, we see a bunch of cosines. Is it okay that we're seeing cosine? Well, the answer is yes. It is fine that we're seeing cosines because this is an even function, and with even function, the Fourier series should have cosines. So that's a good sign. Where is the DC offset? Do we expect to see a DC offset? Well, if the signal is an even signal like this one here, you can project it on this axis. It is an even signal. A DC offset is possible, but you have to find the A naught, and A naught is essentially the average of the signal. So simply by looking at it, the average is here, it's 0. And if you don't trust me, you could basically just find the area here under this half triangle, the area here, and the area here. So you notice this is a negative half triangle area. This is a negative half triangle area. So that's one negative triangle area. This is a positive triangle area. So you add the negative to the positive, that's equal to 0. You divide by 2, and that's 0. So the DC offset is 0, and that kind of makes sense. The key things that we observe here for this triangular waveform is as follows. Is that similar to this one, only the odd harmonics are relevant. So 1 F naught, 3 F naught, 5 F naught, 7 F naught, so on and so forth. The even harmonics, they have no relevance whatsoever. They have a value of 0. So they don't play any role in this signal. The other thing that we observe is the following, and this is important, is that the importance of higher harmonics as the harmonic go up, 7, 9, 11, 13, 15, 17, as you go up in the harmonics, the value of the power diminishes, right? Because the peak value, and maybe I shouldn't have written this because you might think this is what I mean here. This is like a different peak. The overall peak value of each sinusoidal, it goes down with a power of 2, with a square of 2, right? So you take the harmonic value and you square it, whereas here we don't square it. So basically the power of each of these harmonics is even smaller, right? It becomes less relevant. Here, the harmonics are still relevant because it goes down, and it is inversely proportional, but it's still, it's not to the power of 2, right? Here is to the power of 2. So that's another observation that we could observe. That higher harmonics will become quickly irrelevant. Here, higher harmonics are still relevant for up to a certain degree. Here, they quickly become irrelevant. The other signal that I'd like to show you is the sawtooth signal. So you might think it's a triangle signal, but this is not a triangle signal. It's sawtooth. So just look at the picture. They're not the same, right? I'm sure you've seen a sawtooth in other courses in our school and in your program. So this is how it looked like. This is the period, and the period keeps repeating. Now, if I ask you, is this signal, this sawtooth signal, is it an even signal or is it an odd signal? Well, clearly it's an odd signal because you are able to project with respect to the origin, not with respect to the to this axis, the amplitude. So this is an odd signal, and therefore, if it's an odd signal, right away we know that we should not have a DC component, right? A DC offset should not exist, and the expansion should be based on sines, not cosines. So let's see what we get. So if you try it, this is what you get. You end up getting something like this. So that's that, and that's the result that we get. Also notice that the signs alternate between minus and plus, but this does not mean much in the sense of moving to the frequency domain. We look at the amplitude, so even if it's negative, you do the absolute value, so you still get a positive value. And the key result, I guess, that we can observe here is that all the harmonics are important. You see, we take F naught, 2F naught, 3F naught, 4F naught, all the harmonics. This is the first time that we see a signal where all the harmonics play a role, right? So this is kind of remarkable. It's actually interesting. And this is the case because this signal is actually a complicated signal. It is not an easy signal. It is a complicated signal. The more complicated the signal waveform shape is, the more, I guess, harmonics you'll need, right? So it has a sudden jump, even more so than this one, and therefore all the harmonics are relevant. And that's kind of the key result that we get here. That's it for now. Thank you for your attention, and good luck with your studies.